please carry yourself away from your laptops and your iPhones. You want to close that, you won't need it. The backbencher there too. Could you close the laptop, please? Excellent. Okay, a couple of things before we start. The screencast for lecture 1 will be available online this afternoon, and it will likely also one from today. It takes a while to do the rendering, and didn't get the time to do that up to now, but it will be there this afternoon. Then the ones who are on a Mac, they need to have a little bit more patience because I'm in the midst of transitioning from state of 14 to 15. I have the codes that you need for 15, so if you are on a Mac, if you wait a couple more days, then you can get state of 15. In principle, it doesn't matter so much. All the stuff that we do here, version 8 will be fine as well. But nevertheless, you can get the most recent one. Should be there, I would say, after the weekend or so. And if you still haven't completed the survey, there still are a couple out there who did not, then please do. You need the data to work with, and I think we have close to 200 or so people registered, and we need them all. Okay, so just a brief reminder, the aim of the course is I give you data to work with, and you do something that makes sense. That's the whole idea of the course, and in the end, we should all be able to do it. But before we go there, I need a little bit of a run-up before we go through all these separate tests that we're going to cover. There's chi-square tests, exact tests, t-tests, heteroscedasticity tests, all kinds of tests, and there are a lot. And the good news is, in principle, the whole idea of these tests is the same across all of them. What I'd like to do today is try to make sure that you understand what that logic is, so that in principle you can figure out in the end for each and every statistical test how it works, what it delivers to you, even if you have no clue what the actual statistics are behind the scenes. Because for most of the tests that we will consider, I won't go into the details of the statistics there, but you have to be able to figure out what it is that is being tested and what the result is. And that general logic will actually be the same across all the tests, and that's the aim for today. This is a complicated lecture. Easy to get distracted here, but if it works, then you're good to go for all statistical tests, and that needs an extra slide. In principle, this will allow you to understand output of all statistical tests without having to go into the details of any of the statistics. Okay, so kind of a strong statement, but as soon as we're done, it should be relatively obvious. Let's see how that works. This is the argument that I'm going to need, and in the 90 minutes to follow, when I get lost somewhere halfway, then perhaps you remember that this is the thing that I'm trying to get across. First is, well, if you want to have a statement about the population, then that's what you normally want. You're trying to figure out for all the people in the Netherlands or in the world or what have you, what's going on, then, well, one thing to have would be data about the whole population. And you can make all kinds of statements about what's going on because you have the whole population. Disadvantage is normally you don't have it. Or that would be, well, a neat second. If you would know what the underlying process was, so the generating process of the data, then you would also make all kinds of statements about what's going on in the population. And this we normally also do not have. So it looks like we're sort of lost. We need the whole population here, or an idea about the underlying process, and have neither. What is going to save it? Well, two things. First, looking at differences between groups, for instance, in terms of the means. So we look at differences on average. And you may have wondered why we normally do this, but let's say boys score higher than girls, perhaps, in terms of the grades that they get on average. Okay, where is that on average coming from? Well, we need it because that will allow us to use what's called the central limit theorem. And the central limit theorem is what's going to save us, basically. This will allow us to do inferences on samples, even when we do not have the whole population. That's the aim of today. Okay, just a brief reminder. The stuff that you, in principle, need to do more or less now, or should have done. These kind of basic commands in Stata, getting Stata installed and getting it to work, looking at different variables, getting summaries of variables, getting descriptives of all the variables, getting a code book, generating new variables, and generate different kinds of plots. This is what it looks like from a distance. Type command, in this case for age. Summarize command, also for age. Descriptive commands for all the variables that have in the data. And here a summary for age without the details in it. But these kind of things you have to be able to reproduce on the fly. This doesn't involve any testing just yet, but it is useful to be able to have a look at the data. And these kind of graphs should also be relatively straightforward as soon as you have memorized what the commands are. So this is for histogram, you get this. This is for a box plot, you get that. And this is for a scatter plot, you get this if you type that one. This is all in chapter 5 of the book. Just browse through these kind of things. All that will be useful as soon as you get data to work with, to look at the data and see what's going on in the data before any actual testing is going on. Okay. Yeah, then one of the things that I'll talk about in a minute. If you look at these kind of things where you have the detailed option for the summary statistic, this is a variable called soccer score. It doesn't matter what it is. Here you see that you get the mean, but that is nothing new because you got that before as well, even when you do not get the details. But you also get something here, the 50th percentile, or the median, another measure of how where is the midpoint of the distribution here. And some more things here labeled variance, skewness, and kurtosis. And we'll see that back in a minute. So all these extra things that you get, they have actual use, and we'll see how that goes. Another one that you cannot see from this is another measure that you often see, called the mode. That is the value in the data that occurs most often. And in this case, you can see here, but the only thing to do here is simply check the frequencies. For this variable, take some variables, values 0, 1, 2, 3, 4, 5, 6. You see that number 5 is the one that occurs most often, which implies that the mode is 5. It would be nice if there was a give me the mode command, but it's not there. You simply have to look at the frequency. Okay, all small stuff, and we're trying to do this, get across the general logic of hypothesis testing, and I'm going to need that a couple times along the way, because it's easy to forget, and I'm on my way to do exactly this. Okay, first, the claim is sampling in itself is easy. You have a big population, and you sample from the population, and you get a small sample of data. The data we can work with. If you calculate on the sample, no problem. But if you want to learn something about what that says about the whole population, difficult. So this is the standard picture that goes with that. We have the population, let's say all the people in the Netherlands that we want to be able to say something about. We sample a little bit from that, and then we want to say something based on what we calculate here. The red stuff is the only thing that we have about the orange stuff over there. And that process, going from there to there, is called statistical inference. And let's see. Oh, what's that? Anyhow. Any calculations there are straightforward. If you want to calculate what is the mean in the sample, you add all the numbers and you divide it by how many you have. Easy. If you want to know, okay, given that, what was the mean in the population? Complicated. Now you need the statistics, now you need the probabilities, and so on. But not the statistics is actually necessary just yet, as long as you calculate the sample. Okay, one rule of thumb that you need to know. My favorite example here, this is from a television program called Keuringsdienst van Waarde, where they looked at the use of what's called analog cheese. Analog cheese is, it looks like you buy in bulk, it looks like cheese, but it isn't. Actually, this is palm oil and starch. And it costs close to nothing. So what quite a few producers do, they put that on your pizza. You can make slivers of that sort of look like cheese from a distance. And they add a little bit of real cheese, really tasty. And then it's very cheap. And they can put on the package, well, there's starch in there and palm oil, so that will be in there anyhow. And there's cheese too, a little bit. And now you think, wow, it's a very cheap pizza, $1.99 for a margarita. Now why? Because there's hardly any cheese in there. Sometimes even no cheese. Okay, so what they did was they sampled, well, 11 products and tried to figure out is there analog cheese in there? A couple of pizzas and lasagna and so on. And they found, what was it? 5 out of 11 or 45% contained analog cheese. Okay. Easy calculation, 5 through 11, 45%. For the sample, but I'm not interested in the sample. The sample is obvious. I'm interested in the population. So I want to know in this supermarket, given this estimate here of 45%, how likely is it that the products in the supermarket as a whole contain analog cheese? And given the 45, I need a 95% confidence interval. More about what that is in a minute. So let's say a reasonable estimate of the true value in the supermarket of the products that contain analog cheese. You can think for yourself, what sounds reasonable is that you have a sample size of 11. Anybody who feels these kind of things knows the answer? No, obvious normally. The rule is actually quite easy. The rule is 1 over square root n. That is the distance to the left and to the right from the mean that you have, that you should take. So here we have 45%, and the answer is going to be 45 minus a bit to 45 plus a bit. We're trying to figure out how large that bit is, and that bit is 1 over square root n. So if you have 11, and 1 over the square root of 11, not sure how much that is, but that's 1 over 3 and a bit, I guess. So about 30% or so. So 45% minus 30% to 45% plus 30%. That is the confidence interval that you get. As you see with the sample of 11, then you get a huge confidence interval. Anywhere between 50 to 75% would be a reasonable estimate. Okay, so this works if you have something like this where you have either a yes or a no. Is there analog cheese in there? Yes or no? And then that 1 over square root n rule will work. You do it the other way around. If n would have been, let's say, 100, then we have here 1 over square root of 100. That's 1 over 10. That's 10%. So then the confidence interval would have been 45 minus 10. That's 35. 45 plus 10. So from 35 to 55. You can also see that if you want to have that really, really precise, plus or minus 1% or so, that causes that you need a huge sample size. The sample size will go up pretty fast, faster than you would like. Because with 100, it's still plus or minus 10%. With, well, let's see, 900, that's 1 over 3. That's, let's say, 3%. So we need a sample of 900 to get the confidence interval minus 3% plus 3%. And then you need to do a lot already. Okay, so this is an easy way to do it. The rule is not exact, this is just a rule of thumb. And you can calculate this actually in Stata more accurately if you want. But it's good to memorize these kind of things just to have a bit of an idea, sort of a feeling for how large the sample size should be. This is another one that we had in the data collection. Actually, I shouldn't mention it here because the data collection is not complete, but let's see, can I increase this a little bit? That is not very useful because now the edges are gone. Here the example was slightly different. The Dutch Road Assistance Club, ANWB, sampled something and found that 10 out of 25 cars, workshops, or 40%, did not correctly repair a car. So, same question. We have 40% here, and we need an estimate of the kind, well, 40 minus something to 40 plus something. What is that something? And in the example, the n was 25. So 1 over the square root of n is 1 over the square root of 25 is 20%. So now you get 20% to the left and 20% to the right. And I see that the arrow is not pointing correctly here. And this is because I changed my slides from portrait mode to landscape for this set, and the arrow didn't work out very well. Anyway, so what we need here is, what was it? 40% minus 20, that's 20, to 40 plus 20, that's 60. So it's supposed to point to the B. Okay. If you want, you can calculate this in Stata as well. What you type is CII for confidence interval immediate, and then you type proportions, because this is a proportion that you're estimating, and you say 25, that's my n, and 10, that's the number of yeses that I had. So I get 25 observations, proportion of 0.4, and here's my confidence interval from 21% actually to 61. So the square root n rule is pretty good. It's off by 1%. It's not too bad. Okay, so that's one, let's say, sense for how we can get from the sample to the actual population. Now, let's see what we normally do here. As of next week, we're going to go through all these separate tests, and we're going to go through a lot. And all of these start from this that I showed you last time already. You need to know what kind of variables you have, and the most important ones are categorical ones and interval scaled variables. Categorical, there is no order in there. How do you show up at the university? By car, by bike, by bus? What kind of classical music do you like, if any? Or what kind of music do you like? And then you get different kinds of tests. I'm going to show you what the tests look like, just to get a feeling for, well, first of all, what it looks like if you do not know what the test is, and nevertheless, in the end, that we should be able to interpret what's going on here. So let's see how that goes. This is categorical by categorical. You need not even go into the details of the variables. What we're going to need for this is a command that says tab. This is the first categorical variable. That's the second one. And then the test that you need. And the only thing to get from this is, well, we get an output table there. Okay, you can have a look at that. The female, no, yes. And would you consider yourself to be better than the average student in class? This is data actually not from this year, but from 2 years ago. And you get something over there. Okay, so the difficult stuff is happening over here, and in the end, as the last thing in the output, you get a number. Okay, that's the number we are going to focus on. Another example here. Here we have a categorical variable with two categories, such as male, female, and an interval scale variable. For that, you need a different kind of command. We'll go through that in detail. It's called t-test. So compare what people think their net income is going to be across male, female. Again, you get output. Some summary statistics here. For one group, you get a mean of 7.5. For the other group, you get a mean of 7. And you could wonder, is that a substantial difference, a statistically significant difference? And now you see, well, you get a couple more. In the end, you get a big bunch of numbers here, and we'll go into the details of what they mean. But in this case, what you need to focus on is that one over there. So again, some tests, you do not really know what it is, but in the end, we get a number, and we're aiming for what that number is. Finally, age and income. Is it true that the ones who are older estimate that they are going to earn less? To interval scale variables, for that we need another command that's called PW for piecewise correlation. And then you get first what the correlation is, and again a number. Now you have to know where to look, because that stuff that we had here, the PR, is not there, and in fact it's this number that you need to look at. So again, in the end, if you ask for the test, even if you do not know what it does, then you get a number, and we need to be able to figure out what that number is. So here we have them all together. So these three commands are all the same in the sense that they're testing something, and they give you a number that says if it's working or not. And if we do something else, multiple regression, we're trying to predict a target variable, your net income, from a bunch of other variables, as in the Netflix example. Then you get tests as well. Again, that P and a bunch of numbers. So you need to know where to look. This is another one, heteroscedasticity test. Again, that P, PR, and the number. So all these tests are the same in the sense that they're testing something, and they give you a number in the end, whether or not it has worked. Okay, so we're trying to figure out how that works. Now, empirical distributions. We need to have a look at that. This is one example from the distribution of income in the Netherlands in 2012. So you see what it looks like here. So let's have a look. We have, let's see, an average of 33,000 euros in terms of income that you can use. And that's the average there. And we have, well, let's see, something that is leaning towards the left, so to speak. It's very unlikely that people earn more than 100,000 per year. if you have the distribution, you could actually check how many are there, or how many are there, about 80. And if you do not know what this looks like, if you want to summarize this, you could say something like, well, the midpoint of that thing, where is it? And one way of looking at the midpoint would be simply to say, okay, let's look at the mean. The mean is somewhere over there, so that's the midpoint. But also look at the median. Okay, I'm looking at the line where 50% of the cases is on the left and 50% of the cases is on the right. Need not be the same, but it's also a measure of, okay, it's about there, that whole distribution. And the mode, this is actually not a measure of where the whole thing is, but it is the one that is occurring most often. In this case, this one, about 20. Okay, so if you know that this is what the distribution looks like, and I want to give you a summary statement that is as short as possible, I could tell you, okay, the mean is over there. And at least you know nothing about the shape, but that's around that point it should be. Same thing for how wide it is. You could come up with different kinds of measures for how wide that whole thing is. If I mention to you it's about here, and it's about this wide, that already gives you a bit of a feeling for what's going on there. And one standard way to look at how wide it is, well, look at the maximum and the minimum. I could tell you that. The minimum is this, the maximum is that, and the rest is in between, necessarily. That would be one way of telling you how wide it is. Or I could look at these two. P25 is 25% of the cases is on this side, 75% of the cases is on that side. Okay, let's look at that line. And here P75 is 75% is on this side, 25 is on the other. And that is also a measure for how wide that whole thing is. And the standard way to look at it is through standard deviation. That is the average of the squared distances to the mean. We'll look at that in more detail later. What you could do is, okay, if the mean is right there, I could look at all the cases that I have in my data, measure how far away it is from that mean, and square that number, and add that all up. And that is also a measure for how wide the whole thing is. Okay, so this is really crude. If I want a summary statement, okay, it's about there, and it's about this wide. And you could go on and come up with additional suggestions about what the thing looks like if you do not have the data complete. And what you can do, if you have the complete empirical distribution, excellent. You could do something like, how many cases are there that have income marked in 72,000? If I sample 100 out of these, then how likely it is that there will be 20 between 20,000 and 50,000? If I have the empirical distribution, excellent. I can do all the math that we need. Yeah, there's one problem. We don't have the whole population. So we have to do with what we do have, the sample, a small bit of the whole population. And what we could try to do is, well, you could look at the characteristics of the sample. Where is the sample? Where is the midpoint of the sample? How wide is the sample? And then hope that these characteristics carry over to the population as a whole. I don't have the population, but the midpoint of my sample is 32,000. So that might be a reasonable guess for the population as well. The thing is this wide in my sample. All right, can use that as an estimate for my population as well. Okay, so let's see, this is the empirical distribution, not in our data, but in a similar data set from 2 years ago. So here we ask for what do you think that you are going to earn a couple of years down the line. And first you need to recode that thing, because we see that we had values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 16 for the different categories that we had in the data. And these different categories corresponded with different values. So for instance, net income equal to 1, that would be saying, I think that I'm going to earn somewhere between nothing and 1,000 euros per month. 1250 would be something like, I think I'm going to earn something between 1,000 and 1,500, and so on. So first I recode this variable. I create a new variable here called estimated income, and I fill it with all missings. So now I have a new variable, it's labeled estimated income, and it has nothing in it. And now I start replacing these values. Replace estimated income as 500 if net income is equal to 1, and so on. And this whole process, in the end, gives me a new variable labeled estimated income, now with the correct values in there, representing the numbers that you have answered. Okay, here is just a convenience command. I make sure that estimated income, that new variable, in my list of variables is right after net income. I drop the original one. You don't necessarily do that. and I give that variable a label variable estimated income, the net income estimate at 35 years of age. Okay, here you see a summary of that. You see that the 50% mark here, so 50% of you is below 3750, 50% is above. First of all, with 3750 times 12, so you're guessing that you will be above the mean in the Netherlands, which in all likelihood should work out. The mean, in fact, is even higher. It's 4200. So take that times 12, which ends up being quite a decent salary at age 35. Actually, a little bit on the high side, I think, but you know, I hope it all works out for you. And you see here that, well, even looking at this from a distance, this is not exactly the same as the one that we had from the CBS, right? So that's relatively obvious. There were a couple of people in there, by the way, who said, I have no clue, and I replaced those with missing. Just to, yeah, it's actually quite important to show. Yeah. Let me mention this a bit more explicitly. This one over there, net income equal to 16. This is not higher than 15,000. This is when people said, okay, I have no clue. And I replaced the estimated income there with a dot. And a dot in Stata represents a missing value. Okay, so let's look at a couple more of these empirical distributions. Well, for some of these, actually for many of these, we have only a couple of values, like this one here. Only 5 different ones. Or there, what's that? This is a variable. I have very warm feelings towards almost everyone. Wow. Has only 5 categories or 6 categories. Here, same thing, just a couple. So for all these, you could come up with measures for where's the midpoint, where's the center, how wide is that thing, and perhaps also what is the shape of the whole thing. Okay, so let's see. For center, I already mentioned the things that we could use here. And typically what we do is we look at the mean. So are males taller than females? If you ask that question, you're not asking are all males larger than all females, right? You're asking on average, what is the case there? Do young people own more gadgets than old people? Not do all young people own more gadgets, but you want the average. And there are only a couple of exceptions in real life that I can think of where you do not compare means, but instead compare something else. Anybody can come up with an example of that? So if you are comparing two groups on how well they do or what they have or how they score, what would be a typical example of a case where we do not look at means? Any clue? The example's obvious if you know it. If you don't, it's hard to find it, I think. Is that a hand? Yeah, go ahead.
Is your favorite food or something like that?
Sorry, Win?
Your favorite food or something like that?
Okay, your favorite food is the suggestion, and what is the underlying question then, where the mean is not working out?
Because everyone has a particular sort of food or something like that.
Yeah, but okay, what would the question then be? So here, questions are, let's say, are males taller than females. And now we're asking everybody, what's your favorite food? What's the question? Yeah, I mean, the only thing that I can think of is, I don't know, what would that mean? Boys like apples more than girls do, and then it's again on average. I can imagine that you just want to look at what do people like, but then there is no comparison between groups. Any comparison between groups that we do not look at everything? Yes?
How many kids your family has? Because you have to have all the kids.
Yeah, but still. If the question is how many, then we're just counting, right? So I want to know how many kids do people in the Netherlands, let's say, have. I can count them all, and then I can make a distribution. Okay, there are this many that don't have any children, this many with 1, with 2, with 3, with 4. But if I want to make a comparison between groups, I don't know, do foreigners have more children than Dutch people? Then again, I sort of have to look at these averages, even though I know that 3.3 children cannot have. Yes. Sorry, identity. Yeah. Yeah. Okay. The example is if you look at the numbers on your passport, then you could still ask, okay, do let's say boys have higher numbers on their passport than girls? But if you want to test this, then still I think you're sort of stuck with on average. The only thing is, it's a totally weird question, and you would not expect, I think, that there would be a difference. Perhaps it is, I don't know. It might be different if you're a boy, the first digit is different than for girls. Actually, I'm looking for the cases where the means themselves are not the ones that you're interested in, and the standard, yes.
So what's the most frequent comparison?
No. Mean comparison. One type of comparison where this is not working through means is in all kinds of contexts. We know who plays soccer best, Germans or the Dutch. Well, I think it's pretty obvious at this point, but in principle, we're not going to check, okay, for all the Dutch on average, do they play worse or better than the Germans on average? We're trying to find the best ones, and we compare the best ones with each other. They were not looking at the mean at all. So all kinds of contests, the mean is not the thing that you're aiming for. And for all other things, almost all, you typically do. Let's see. We have that. And the fact that we use means here and not something else is because we need it. Okay, so let's see. All these are on average. Perhaps one thing that you can briefly elaborate on is the one that I didn't elaborate on before. If you're female, then you are more sensitive to alcohol. Just in case you wonder why that is, does anybody happen to know why that is? Body weight is one suggestion, but it's wrong. Anything else? Or you think that more practice might be good? No? Yes? Body fluid?
Yeah, I read this somewhere.
Yeah, it might be, but I don't think it's that. No, this is not.
Because male liver processes alcohol faster than women's liver.
The suggestion is that male liver processes alcohol faster than a female liver. And it's close, but if you would have said stomach, then you would have been actually correct. So the difference is in the stomach of boys. Yeah. Okay. Need 2 minutes for that, but nevertheless, now that I started, I have to finish. So the idea is if you drink alcohol, then first it lands in your stomach, obviously. Then some of the alcohol there gets removed, and you don't know exactly where it goes, but in any case, you're not bothered by that bit of alcohol. Okay? You do not get drunk because of that. Then at some point, it passes on, and the alcohol reaches your bloodstream. And when it does that, then you get drunk. Okay? So the longer it stays in your stomach, and the better your stomach is to get the alcohol out at that point in time, the less likely it is that you get drunk. And we know that for females, that stomach part is working, let's say, less effectively than for males. So that also means, for instance, if you would inject alcohol in the bloodstream, bypassing the stomach, then the differences between boys and girls are gone. Okay? This is one of the tests of the whole argument. And the other thing that you can get from this is also why you get drunk more easily if you haven't eaten before. But if you have not eaten before, then whatever you drink will pass your stomach fast and will enter your bloodstream. If you have eaten something that's very fat and it's a lot, and this will stay in your stomach longer, your stomach won't open at the bottom point. If you keep adding alcohol on top of it, as long as the food is there, making sure that the alcohol cannot pass, you do not get drunk so fast. Okay, so if you want to get drunk fast, you Eat a lot. Okay, anyhow, but I didn't want to talk about that at all. Let's see. There are two things to mention about the actual empirical distribution, about where is it and how wide is it. And there is more. The third and the fourth one that are typically used are called skewness and kurtosis. This is skewness and this is kurtosis. Same picture, but now a little bit bigger. Skewness is it leaning towards the left or right? And here, this is something that is completely symmetrical there. We have a skewness of 0. This one is skewed to the right. I always have to think a couple minutes before I remember which one is to the right or left. But if it's tilted to the left, then it's skewed towards the right. So if it's leaning in that direction for you to the right, this is skewed to the left, and this is skewed to the right. And you get actual numbers for that. And kurtosis is the extent to which the whole thing is peaky or flat. So the skewness is leaning toward the right or left, and the kurtosis is it very peaky like this, or very flat like that. And there are even quite complicated words for that: leptokurtic for peaky, and platykurtic for not so peaky. And this one, kurtosis has an actual value of 3 if it is the same as the extent of normal distribution. Okay, so we have, it's about there, it's about this wide, it's tilted towards the left or right, and it is rather flat or it's peaky. 4 of these numbers will actually summarize a distribution quite neatly. If you're into the actual math here, this is the easy bit, the mean. We add them all up and we divide by n. I forgot the divided by n. Yeah. Variance here, differences between the mean and the actual cases that we square and then add all up. Square root of that is called the standard deviation. And now we get into something more complicated. We have moments, as they are called, defined like this. I don't want to go into all the details here, but skewness and kurtosis, in fact, are defined in terms of these moments over there. If you're into the statistics and into the actual formulas, you can look at them there. Okay, so we have a list of numbers. That's non-summarizing the data would be, this is a long list of numbers. Summarizing the data would be, okay, let's look at a histogram, or let's look at a midpoint, the spread, and the shape of the whole thing. Okay, that's all about empirical distribution. Now the theoretical ones. The easiest example there is the ubiquitous coin flip. So here we see if we flip a coin 50 times, how likely is it that, for instance, we get 25 heads and 25 tails? Well, the probability of that is 11 and a bit percent. From all the things that can happen, this is the one that is the most likely, but even that one has only 11%. You expect from 50 flips to get 25 heads, and if you want to do the calculations, the probability of X heads, if you flip 50 times, is this thing over there. You can do the calculations if you want. So if you know, okay, the generating principle is we're flipping a coin here, then I can try to figure out all the different kinds of probabilities relatively easy. Okay, so one theoretical distribution that you need to know more or less by heart is this one, this hump you must have seen before. This is called the normal distribution. There is an actual formula for this, looks like that. And what you need to know from this one, also called the bell curve, this is the standard normal distribution, where standard normal means the midpoint over there is at 0. And the standard deviation of the whole thing is 1. The plus 1 sigma stands for plus 1 standard deviation to the right. So you can see that if we go, let's say, 2.5 standard deviations to the right, then there is not much left there. If you go 2.5 standard deviations to the left, there's also not much there. So you could argue here that normal distribution, almost everything is between minus 2 standard deviations and plus 2 standard deviations to the right. And the crucial thing here is, even though this could be anything if you look at it, given this formula, you see that the only two things that are in here are mu and sigma. Mu is the mean, in this case 0. Sigma is the standard deviation, in this case 1. So that whole bell curve is completely defined by only two characteristics, mu and sigma. And if you know that, then you know basically everything. Okay, this is just one example and the one that is best known, but there are a gazillion more. If you go through Stata, there are lots of these kind of things that you can actually calculate with. So you have the double exponential, the gamma distribution, the 2p lambda distribution. For all of these, there is a formula that fits it. Normally we'll only focus on the normal distribution, but in principle you can do the calculations for all these different kinds of distributions. Yeah, and that's the thing to get from that. If we would have a theoretical distribution, and normally we don't, but then we could run calculations as well. Well, perhaps not by ourselves, but you can put it in Wolfram Alpha, as I just put the other thing over there. And let's try to see how that works if we do that standard coin flip example. Because that way of testing a hypothesis is actually what's going to work for us in helping us understand all the other tests. So, we're flipping a coin, and we're flipping a coin how many times? 1,000 times. So let's see how that goes. Here is a little bit of Stata code that I have there in larger font. This is, you don't need to know how this works, but this is actually simply simulating 10,000 runs of 1,000 coin flips, just to see what could happen. And what I get from that is this. So if I do this flipping of the coin 1,000 times, 10,000 times, most of the time I get something that is near 500, as you would expect. Very, very rarely I get something that is near 450 or near 550. And here you see how likely the other numbers are in between. So what we're trying to figure out here is, that's usually the question, do we have a fair coin here, or is there any evidence that the coin is not fair? And the thing to do would be simply, okay, let's flip the coin 1,000 times, and let's compare that number what we get then with this distribution. You know that this is more or less what you can expect. And if I get a number 600, then it's pretty obvious, okay, this is not very likely to have resulted from a fair coin, because this is what the distribution would look like if I would have had a fair coin. So the question is, where can I start thinking, well, we usually take 5% of the standard breakoff point. Where is the number, somewhere over here I think, so that I can say, well, 5% of the cases is over there, and the other 95 is on the left. And we're looking for that now. Okay, let's see, that was the code. So now the standard hypothesis testing terminology that we'll use here as well and for all other tests too. First, we need what's called an H0, a baseline hypothesis about the world. And all these baseline hypotheses are the same in the sense that they have some kind of equality in it. In this case, the H0 would be the probability of heads is 0.5. Or the probability of heads equals the probability of tails. There's an equality in there. That will allow me, in this case, to create that distribution. I know what the distribution would look like if indeed H0 would be true. Then I have alpha, that is the probability of rejecting H0. Okay, I don't think that the coin is fair, when it actually would be true. How likely is it? If H0 is true, that I get data as I have, or data that are even further away from H0. So in this picture, we're looking at 5% over there. If I'm thinking perhaps the coin gives heads way too often, I'm looking at, well, I'm willing to take a risk here. If I really want to go, let's say 100% certain, then I have to be over there. You're never 100% certain. So I'm sticking to 95% certain. I'm looking for the 5% over there where I'm willing to take the gamble. Okay, it's extremely unlikely. It's so unlikely, the probability to get that is only 5%, so forget it. I don't think that this coin is fair. And then if we get a value there where we find that alpha is smaller than that 5%, so I get, more back over there, let's say a value there, okay, 555 is over there. There certainly is not 5% of cases over there anymore, so I get a value of 0.0001, for instance. And now I would say, okay, I reject H0. It's extremely unlikely that this would happen if H0 would be true. And we could use the cutoff of 5% sort of, by default. Why not 1%? Why not 2? Why not 7? It's just a convenience. And then the other thing to remember from this, we're testing H0 here, and there are only two things you can say. H0 is rejected, or H0 is supported. Well, if you go for not rejected, that would be fine too, but anything else is not right to say. So H0 is true, or H0 is not true, or the alternative hypothesis is true. None of that. We reject hypotheses or we support them, and that's the only thing you can choose between. The laptop people, it's a good try to clear themselves away as well. Could you poke the guy on your right? Right. Thank you. Okay, so for that coin flipping example, we sort of know how it works. We're expecting from 1,500. We think that the number of heads will be way higher than it's supposed to be. And we're trying to find a number where it starts to become weird. And it starts to become weird when only 5% of the cases would be higher than that number. One small side note, as mentioned during the break, if I wouldn't think that the coin might be unfair in the sense that it gives too many heads, but just wanted to test, okay, is it fair at all? So perhaps it gives too many heads, but perhaps also it gives too few heads. Then I would not check 5% on the right, but 2.5% on this side, and the other 2.5% on the other. This is actually the difference between what is called one-sided and two-sided testing. So if you have no clue, it might be an unfair coin, might be back in that direction. Then again, I'm using 5%, but 2.5 on that side, and 2.5 on that side. Any questions up to now about this part? If you have a question, you won't be the only one. Just be daring enough to say it. All right? Okay? Sure? You had rejection and being supported, and that's pretty much it. And this is actually a bit of a nuisance because you get a bit less than you would have hoped, perhaps. You can see this here. For instance, suppose that you find that the number of heads out of 1,000 was 511. In that case, H0 will be supported, in fact. You see this in the graph over there. 511 is about there. So this is, let's say, totally realistic, given a fair point. So then H0 will be supported, and you might be tempted to say, that means H0 must be true, the coin is fair. But this is typically not the case. You cannot have that, because there are many other H0s that would also have been supported. For instance, the probability of heads is 151, so slightly more than half. That by and of itself would also have worked. You would have created the same kind of shape there, and then still, the 511 would be decent. So H0 heads equal to 0.51 would also have worked. And that is in fact how the confidence interval is defined. A 95% confidence interval, but it's a set of H0 values that would all be supported at alpha equal to 5%. And you can calculate that number in Stata, again through the command that we saw before. Confidence interval immediate for proportions, 1,000 cases and 511 are heads in this case. Then what we see is, well, the proportion is 0.51 and a bit, and there the 95% confidence interval is running from, well, 0.48 to 0.54. So any H0, even the probability of heads is 0.54, would also be supported. Yeah?
What kind of testing would you like on your confidence interval?
Normally, what you would like for any kind of confidence interval is that it is as small as possible. If my confidence interval is really, really small, that would imply that I'm really, really certain about the value that I have. Or stated differently, if the confidence interval is very wide, think about that analog cheese example. You have 45%, and if the sample would be even smaller than that, let's say, 4 is really small, you get beyond the boundaries, so let's say 9. 1 over the square root of 9, 1 over 3 is 33%. So then we have 45 minus 33%, answer there was 3.5. There is no acceptable range here. You have to decide, if it's about analog cheese, you have to figure out for yourself beforehand how precise you want to have it. If plus or minus 10% is good enough for you, excellent. Take n equal to 100. If you want to be closer than that, then you need a larger sample size. That's not a statistical question, actually. It's simply what you want to know, how precise you want to know. Okay, so let's see. This is how it went. We hypothesized something about the world, in this case, probability of having 0.5. Then we get a statistic, something that we get from the actual experiment with the coin flipping, that tells us something about how likely it is that H0 is true. In this case, this is the number of heads. Here we had this example 525 out of 1,000, and now we have to determine how likely is it that we get that 525, given that H0 is true. We figure that out. Luckily, normally we do not have to figure that out by ourselves. Data will do it. That's the number that we are getting at the end of every statistical test. In this case, we were able to do this. We simulated this thing, and then found out what is rare, all the stuff over there, and what is pretty standard, the stuff that's in the middle. And then we can determine if 525 is unrealistically high given H0 or still fine. And if we find that it's the probability that we get a value like that is smaller than 5%, we reject H0. Then still we can make mistakes, because it's possible that we end up in that 5% region. But nevertheless, we're willing to take that risk, and we say we reject H0 in this case. Okay, that principle will work for all tests. And they all go like this. Same slide in principle, but now forget about the whole coin flipping. We hypothesize something about the world, and we call it H0. And that could be boys score equally high as girls, has an equality in it. The mean for boys equals the mean for girls in the population. It could be anything else. And then the data give us some statistic that suggests something about how likely it is that that equality is true. So one example would be if you think boys have the same high school grades as girls, then we look at the mean for boys and we look at the mean for girls. Here we see 6.5, here we see 9.5. That difference is likely to say something about whether or not H0, they are the same, is true. Luckily, the statistics is done behind the scenes. We need to determine somehow, Stata does, what kind of distribution of means we would typically get. And we got that in the coin flipping example by doing the simulation. We can get it as well if we do some statistics, or Stata does. And then as soon as we have that, we determine, okay, assuming that H0 would be true, then how often would it occur that we get data like this, or something that's even further away from H0? If that value is below 5%, we reject H0. If it's above, we do not reject it or support it. Now, it may look reasonable, but it doesn't look like a real solution just yet. We can do this if we have a complete empirical distribution. Great. But if we would have had that, then there is no statistics necessary. I have all the data that there is. Or if we have some weird theoretical example where we are flipping a coin and we know that the guiding process is, it's 0.5 for every throw that we have. And we have neither of these. So it still looks like it's not working very well. For instance, something like this. Well, here we have girls and boys, and this is the extent to which they like classical music. We have no idea about what the population distribution looks like, and we certainly see here that this is not resembling any distribution that I know, certainly also not a normal distribution. That would be a totally different shape here. So there is nothing that I can do here. It doesn't look like anything that I know. However, to the rescue, we have what's called the central limit theorem. And this is the reason why we consider differences in terms of averages. The central limit theorem says this. This is the complicated version. If we have, let's do the complicated version first. If we have n independent random samples, and we calculate the mean of that random sample, then what we will see is, if that sample is large enough, the distribution of means will have a standard normal distribution. In red, the more loosely defined central limit theorem, the mean of a large enough sample from an arbitrary distribution typically has something close to a normal distribution. And that's a good thing. So if we have a big sample, lots of boys, lots of girls, and we take the mean of something that we measure on that group, the distribution of that mean will look like this. And that's kind of nice because that normal distribution, we know everything about that. And this only works for the mean. So this is also why we look for the mean as the midpoint of a distribution. We could use the median or something else, but then we do not know, we don't have the central limit theorem. So we use the mean because it works like this. You might recall that that bell shape that we had in the coin flipping example. Do we have that here? There. We didn't talk about it at that point, but this looks like a sort of normal distribution, and this is not a coincidence. So we start out with something that has 50-50, so that doesn't look like a normal distribution at all. But if I flip a coin often enough and I look at the mean across a large sample, then I get something that does look like a normal distribution. And that's not a coincidence. Okay. You might wonder, could we do the math just in a minute to show why that central limit theorem is actually working? Don't want to go there. This is the shortest proof that I could find. And you can see this is, it's not trivial. Okay? This requires some serious math, and there are, if you look online, I think 100 or so different kinds of proofs. Most of them longer than this, but none of them easy. Okay, so this is not something that you do on a Saturday afternoon. Actually, I prepared this. Yeah, so here you see that this thing indeed is not normal by coincidence, but normal through the strength of that central limit theorem. And even here, you could do the same thing. So now we know, this girl group and this boy group, if the sample of that is large enough, and we look at the mean of this variable, the extent to which you like classical music, that thing will also have that bell shape. And if it has the bell shape, we can do the calculations, and we can figure out if there is a difference between two groups. Okay, so we're steering away from the abyss there. The mean of a sample approaches a normal distribution. Do realize that this is, I sort of make it seem as if this is coming to the rescue, and it is, but the statement in and of itself is sort of weak, right? If the sample is large enough, where large enough is not defined, okay? So this, in a way you could argue, if you are really picky about it, this doesn't help us so much because large enough is not defined. At some point, perhaps in the thousands, then it will be close enough to normal. And what we normally do is simply that and hope for the best that it will all work. And that is what's going to help us understand all the statistical tests that we're going through, and in fact all the statistical tests in all likelihood that you will meet in the next 10 years or so. Because the thing to do for any kind of statistical test, even if you have, or precisely when you have no clue what it's doing, you need to do two things. First, you need to figure out what H0 is. There must be an H0, some idea about what the world looks like that has an equality in it. Boys are equally likely to do whatever than girls. This one is equal to 0.3, something of that kind. You need this because otherwise there is no way to calculate the distribution of means that you would expect. And the second thing is, you need to be able to, at some point, figure out, okay, that there should in the end be a number there that I should compare to 0.05. If it's below 0.05, then it's extremely unlikely, if H0 would be true, that I get the data that I have. And if it's below 0.05, then it is possible, given that H0 is true, that I get the data that I have. So there are two things to do. Figure out what H0 is, and there needs to be an equality in it. And the second thing is, find that number that we're looking for here, that will allow us to decide if H0 is rejected, yes or no. Let's see. So these were the examples that we had. It's a bit in small print, but I started out with categorical by categorical. That's a chi-square test. And a t-test here, this is comparing two groups on an interval scale variable, and these are two interval scale variables. So the first thing to look for is what is H0 in all of these cases. Let's see how I can do this. Okay. You need to be able to see this first. Let's see. So let's have a look at this part of the table. This was boys and girls. So the first one are boys, I think. The second one are girls. And here you see that the distribution of boys and girls is 68 boys versus 35 girls. Now what we're checking here is if we have that distribution, so let's say 2/3, 1/3. What I'm trying to test is that distribution, 2/3 versus 1/3, the same across all the columns here? So what I would expect, if that would be true, is 2/3 there, 1/3 there, 2/3 there, 1/3 there, 2/3 there, 1/3 there, 2/3 there, 1/3 there. This is my H0. It's an equality. It's equal to 2/3 versus 1/3 for all the columns. And if I assume that, I can have a test and see how likely it is that this actually works. Here, it's easier. I have an interval scale variable. How likely, what do you think you're going to earn when you are 35? And I have two groups, males and females. The output here already says, well, it's 7.5 for the 0 group, and it is 7 for the 1 group. So I can imagine here that the H0 in all likelihood is both groups score the same. And then the question is how likely it is that if both groups actually score the same on average, that in my data I find 7.5 versus 7. And the other H0 here would be if I have age over there and net income, is it the case that people as they get older think that they are going to earn more or that they are going to earn less? My H0, I need an equality here, would be, well, no. There is no difference. Irrespective of how old you are, you think that you are going to earn more or less the same net income on average. So these are the H0s that go with these kinds of tests. So 68, 35 is the same across all columns. The means for males and females are the same, and X and Y are not related. Or, in fact, here I could say the correlation between the two equals 0 if you're looking for the equality in H0. Okay, what's that? Yeah. Next part, we know the H0s for these three. We're looking for the number. There's the first one, there's the second one, and there's the third. Actually, the only complicated one is the last one. There, a number of 0.75. This is above 0.05. So given that H0 is true, it is totally likely that you get data that looks like this. Yes?
It says is that the probability that your results are true are 75%.
No. By all means, never say the probability that is true. That whole true, forget it. Don't ever say it in the whole course. Forget it. It's more precise than that. If H0 would be true, that is, if the underlying process, so to speak, for all these columns is in the end you're expecting 2/3 versus 1/3. If that is my H0, then the data that I apparently got here is, let's say, totally consistent, totally likely to have resulted from that H0. So what we say here is H0 is not rejected, or H0 is supported.
So what would be your ideal value for B, like 1?
No. There is.
You want to go in that direction.
Okay, first of all, the question is, what is the ideal value for this number over there? There is no ideal value. First of all, it's not that obvious if you want H0 to be rejected or supported. You just want to know what it is. And in principle, all the values here above 0.05 are the same. It all means H0 is supported, and all values below 0.05 are H0 is rejected. So there is no preference for, I'm looking for a 0.9 or there's nothing like that. But just checking if it's above or below 0.05.
Okay, but if it's 0.06, for example, then it's not very strong, right?
Yeah, this is, so the question is if it's 0.06 or 0.04 or 0.05, then what? Because it's, that 0.05 is arbitrary. So if we would have chosen 0.04 as the arbitrary cutoff, then we would now perhaps say that something is supported, even though now we say it's not. And you're totally right. That is an issue, and one of the typical things, well, first, this is sort of a source of debate. The hardliners will say, no, 5% is 5%. If it's 0.06 or 0.0 or 0.9, that doesn't matter. If it's above 0.05, forget it, it's supported. And we're not looking at how high above the 0.05 it is. Most people do not agree with that idea and would say, well, at 0.06, almost rejected, so it might be close. If you would have had a sample that would have been bigger, it might have been rejected still. 0.04, rejected by a hair. So these kind of arguments do play an actual role. And what you, in that sense, there is a value that you would not like. So anything near 0.05 is not what you want, because then it's not so obvious, okay, is it right on the left or on the right of the 0.05? So what you like to have is something that is either close to zero or, let's say, large enough above 0.05 that we're not, wondering about these kind of things. Yeah.
And the PR value that you get is also dependent on the way you formulate your
Yeah, so the question is, the value that you get here, does that depend on how you formulate your H0? Well, in principle, yes, but for all these tests, there is a given H0. These tests are being calculated given what H0 is being used for this test. So it's not that you can come up with your own H0 and then you get that number and that fits whatever you think of. So you have to figure out what H0 is, and you can be wrong, right? If you would have assumed something else here, my H0 is, well, all these numbers here in these cells are equal. That could be an H0, but that's not the one being tested with this test. So you have to be able to figure out what the actual H0 is that belongs to the test that you do.
Yes, and H0 is dependent on the test.
No, it's the other way around. We're trying to test an H0,
Okay. Yeah.
and we do it by looking at that number.
Yeah.
Okay, then the other ones. First, this one, that's the easiest. This is correlation. We're trying to figure out, is it true that as you get older that your estimate for net income at age 35 is, let's say, higher or lower? And here we get a number, it's the one over there that you need to look at, of 0.8. Again, above 0.05, so H0 is not rejected and in fact supported. If there would be no relation between age and income at all, that is our H0, it would be totally likely to get a value like this. It would be totally likely to get data as we have. And the last one, that's the only one that's slightly more complicated. Here you get 3 of these tests, and the thing to remember is that you normally have to look at the one in the middle here. You can imagine why that is. Perhaps if up front I would have an idea that, let's say, boys score higher than girls, then I would have the same thing as in the coin flipping example. I think that it is more likely that boys score higher, so I put the 5% all on one side, as I did with the coin flip. Or all on the other side, because I think that boys score lower. And these two are exactly representing those 2 examples. The one in the middle is the one that we normally look at. I have no idea up front whether or not boys score higher than girls or the other way around, so I'm just checking. H0 is they score the same number, and let's see how likely it is that we get something like we have in the data, 0.49, way above 0.05. Again, H0 is not rejected. So if indeed boys and girls have the same mean, then it would be not weird at all to get data as we get. Even though here is a 7.5 and there's a 7, this could be easily due to random fluctuation. So in this case, we're not rejecting any of the H0 hypotheses. All supported. Okay. And this will actually help you out in the sense that there are only, well, there's basically only one thing to do. If you see any kind of statistical test, try to figure out what H0 was that is being tested. There is an H0 that belongs to the test. You cannot come up with one of your own. And if you can figure that out, then, okay, that's being tested. If you can find the number in the end that is used to actually test it, then you're done. That number below 0.05, we reject H0. If that number above 0.05, we support H0. And that is all there is to it, in fact. So it's actually quite easy when you think of it. There's nothing that you need to know other than what the heck are we testing here? And in the end, there is an answer. Reject it or not. And that's it. Okay, I see that this doesn't bring the same excitement that it brings to me, but it does make it quite easy. Even if you have very, very complicated tests in the sense that behind the scenes, Stata is doing, twists and turns to get that number out for you. In the end, you get a number, and the only thing you have to do is compare it with 0.05. All right, let's see. A brief recap. All data that we get, that we will ever get, are samples, not the population as a whole. Calculations on the sample themselves typically do not involve statistics and probabilities. It's just numbers. I can calculate a mean, I can calculate a maximum, doesn't matter. That's all standard arithmetic. There is no statistics there. The arithmetic changes and becomes statistics as soon as we want to say something about the population as a whole based on that small bit that I have. Then we need to do the complicated stuff. Tests depend quite a bit, crucially in fact, on what kinds of variables are being compared. We had 3 examples here, 2 categorical ones, categorical by interval and 2 interval ones. For these you have different kinds of tests, but the principle behind these tests is the same all the time. H0, and H0 has a equality in it, you need to know what it is. You check the data or you simulate, and in all likelihood you do not even do that, because Stata will do the math for you. And you try to figure out, okay, how likely is it, if H0 would be true, that I get the data as I have, or something that's even further away from H0. That gives you a number. If that number is below 0.05, you reject H0. And then you also learn along the lines that confidence intervals, that are the sets of values for which H0 is not rejected. And you want these confidence intervals as tight as possible. And one way to get them as tight as possible is to come up with a very, very large N. Calculate a sample, collect a sample with N equal to 20,000. Excellent. Now you get really tight confidence intervals. Okay, the fact that all this works, this is due to what's called the central limit theorem. And the central limit theorem only works because what we're comparing are means. If we're not looking at means, then we need something else. And for quite a few of these things, we have something else, so we shouldn't worry too much at this point. But the fact that all this is working is due to that central limit theorem. So, H0, look at the number below, above 0.05, supported, below 0.05, rejected. That's in principle all there is to it. Any questions about this part? Hard to believe that it's so easy, actually. How could you ever fail a course like this? Yes?
Yeah, if you start that, you have this
Yeah.
number in the middle and the numbers left to the left and the right. But,
Yeah?
So what do these other numbers mean? Because would they apply to another H0?
No, okay. Which kind of numbers do you refer to here?
To the left and to the right.
These? Those? Those? Okay.
Yeah.
Any questions? So one at the top. Do that again. Yeah, okay. The ones on the left and right, yeah. These are. These I briefly talked about. These are other tests where you are assuming, this is again the difference between boys and girls. Boys think that they are going to earn a lot more than what girls think they are going to earn. If you have no clue up front, if boys will give higher numbers than girls, and you simply want to check is there a difference, we look at the one in the middle.
Okay, let's say now I had the H0 in the beginning, boys say they earn more.
Yeah.
And then I would look to the left value. But
Yeah.
you run the same data, so can't you just say in hindsight, no, that left value that's higher, so that's more.
No, that is cheap. So whatever. So the idea is, can't I just look at the data and then see what you have here? The boys give higher means there. So apparently, if there is a difference, it must be that boys are the ones who give higher numbers. So I'm going to do a one-sided test, all on that end of the spectrum. No, you cannot look at your data first and then come up with an idea what it looks like. So you can only use the data once. So you think first, and then you look. And as soon as you look, then you cannot say, oh, wait a minute, I've got a different page here. This is cheap. No.
So the left one, the left probability thing
That one?
yeah, the one that says something about another test than the middle one.
Yeah, this is the one-sided test in one direction. This is the one-sided test in another direction.
So this data actually supports all those things here.
Yes. Yes.
And they're always together one?
Together one?
Yeah, when you add
This one and that one?
with that one, it's one.
Oh, so the question is this number plus that number always equal to 1? Oh, that's a good question. It's tempting to say yes, but I don't know. I think it is. I think it is. Yes.
So actually this says that the hypothesis that boys are more than girls is supported, but it's also supported that boys and girls are equal.
No, the H zeros are always the same. The H zeros are equal. For H zero, you need an equal. So you start from the fact, okay, boys and girls with the same numbers over here. And in one case, you're checking that against boys score higher than girls. And in the other case, you're checking that against boys score lower. But the H zero itself is the same across all three tests. And you can feel why that might be reasonable, because if you would have an H0 that says boys score higher, the higher is not defined, so it's not so easy to say something about how likely it is that I'm going to expect some kind of distribution if you're not saying anything about how much higher it is. So for that you need the equality in the H0. Anything